confidence intervals and introduction. If you'd like to see a video on how to find a confidence interval, you can find that 2 videos from now. This is an introduction to the concept. The Pew Research Center took a random sample of 446 registered Democrats in the US in 2013. In this sample, 57% of the 446 Democrats interviewed agreed with the following statement: "The news media spends too much time on unimportant stories." This percentage just tells us about this specific sample. So 57%, we get this number from looking at the 446 Democrats that we interviewed or surveyed. What percentage of the population of all Democrats would agree with this statement? So what's the percentage of all Democrats that would say the news media spends too much time on unimportant stories? In other words, what is the population proportion? We have a sample proportion or sample percentage. What's the true population proportion? In this scenario, note that we know a statistic or population proportion, 0.57, but we don't know the true population parameter p, so we don't actually know what percentage of all Democrats agree with this statement. It turns out in the real world, a lot of the times we don't ever actually know the true value of p. So this p-value we usually don't know because it's hard to take a census and interview every single person. So somehow we're going to want to work with taking a sample and finding a sample statistic or proportion like p hat here, 57% or 0.57, and then we want to somehow make a deduction about the true population parameter that we don't know. Suppose a newspaper wants to run the story, "Most Democrats believe that the news media spends too much time on unimportant stories." Do you think that based on the sample that we just looked at of the 446 Democrats, we could run a news story like this? We found that of those 446, 57% agreed with this statement. Do you think that means that we can say that most Democrats believe in it? Can they run the story? How certain are we that most Democrats feel this way? In other words, based on the sample that we took, where we found that 57% of the people surveyed believe in this statement, how certain are we that all Democrats or every single Democrat believes in this statement? Well, let's dig deeper. Things that we know about this situation. 1, our estimator or survey method is unbiased because we looked at a random sample of people. So the survey of the 446 Democrats was taken, they took a random group of Democrats. This means that our population parameter is probably close to 57%. What I mean by that is that because we had a random sample, we're going to think that probably the true percent of Democrats that believe this statement, if you look at the whole population, it's probably pretty close to 57%, this sample statistic that we found. This is related to some stuff that we talked about in 7.1 through 7.3, so go back to that if you're not sure why. 2, the standard error can be estimated using this equation here. Now this is our standard error formula that we learned previously. So you guys have to look that up. It's a formula for standard error. Now you guys might recall that the one we normally use has p in this spot, not p hat. Remember, p is our population proportion. Now, when we don't know the true population proportion, we're going to use p hat, the sample proportion, to estimate p. We only do this when we don't know the true p. So I'm going to use p hat, or 0.57, which comes from 57%, as our p-value in the sample, in our standard error formula. Now, if we plug 0.57 in here, and then we plug in n, which is the sample size, or the number of Democrats that we interviewed, 446, and simplify, we're going to get 0.023, or about 2.3%. So what does this tell us? It tells us that our standard error in this situation is 2.3%. So we could say we expect, if we expect the true population parameter to be close to 57%, give or take 2.3%. 3, because the sample size is large, the probability distribution of p hat is pretty close to being normally distributed. Also, it's centered around the true population parameter p. Why do we care about this? Let's examine it more closely. Because we know the distribution is normally distributed with standard error 2.3%, By the empirical rule, we can say that there's a 68% chance that p hat is closer than 1 standard error from p. There's a 95% chance that p hat is closer than 2 standard errors from p. And there's a 99.7% chance that p hat is closer than 3 standard errors from p. So the idea is, we don't know what p is. We take a sample of the population and find a p hat. In this case, we did a sample of 446 Democrats and found that 57% believed in that statement we were looking at. Now we could keep taking samples, like do a whole bunch of them. And the idea is that the empirical rule gives us this piece of information about how close p hat and p are from each other. We can take this even further. We can say that we're highly confident that p is between 57% minus 3 standard deviations from 57 and 57% plus 3 standard deviations from 57. In other words, when I say that there's a 99.7% chance that p hat is closer than 3 standard errors from p, I mean that if we take p hat and we add 3 standard errors and we subtract 3 standard errors, the idea is that we're 99.7% sure, or like really confident, that our true population parameter is, within 3 standard deviations below 57 and within 3 standard deviations above 57. If you actually simplify these equations, you get that p is probably between 50.1% and 63.9%. In fact, we're like 99.7% sure of this, or highly confident. So from the empirical rule and our knowledge about standard deviation and p hat and p and all these concepts, you can make this deduction. The range we got in the example we just worked out is called a confidence interval. The confidence interval we just found is 50.1% to 63.9%. Often we report a confidence interval as the estimate plus or minus some amount, so we could say 57% plus or minus 6.9%. And if you add 6.9 to 57, you get 63.9. If you subtract 6.9 from 57, you get 50.1. The sum amount, or this 6.9 that you both add and subtract to 57, it's called a margin of error. The margin of error tells us about how far from p our estimate is believed to be. In other words, just to reiterate, we don't know p. We can find a p hat by taking a sample and finding a percentage. In this case, our p hat is 0.57. As a percentage, it's 57%. Our goal is to know what is the true p, like what's the population proportion in this instance, like what percent of all Democrats believe that statement. We don't know what it is, but we can kind of like narrow down where we think it might be when we take our sample. In this case, we think that the true population proportion, or percent of Democrats that believe in our statement, is probably between 50.1% and 63.9%. We're confident at a level of 99.7%, so we're pretty confident. A confidence interval tells us two things. One, a range of plausible values for a population parameter. So in our example, the range of plausible values for Democrats that believe in that statement, if you look at all of them, is 50.1% to 63.9%. It also tells you a confidence level, and the confidence level expresses our level of confidence in this interval. So in our example, because we looked at 3 standard deviations below and 3 standard deviations above, and we know by the empirical rule that 99.7% of stuff in our distribution falls within that range, we can say our confidence level is 99.7%. We're pretty confident. Note, if we had used 2 standard deviations instead of 3, our confidence level would be lower. It would be only 95%. So still pretty confident, but not as confident. Let's examine this more closely. When we just did this example and said we were highly confident that p is between 50.1 and 63.9, I meant 99.7% confident, and I just noticed that I misspelled this, so that should say confident right there. Now, if we do this for 2 standard errors instead of 3, what we would do is we would subtract 2 standard errors, or 2 times 2.3% from 57, And then we would add 2 standard errors, or 2 times 2.3% to 57. And we would get a new confidence interval. We would get the range from 52.4% to 61.6%. In this instance, we would say that we are 95% confident that the p-value is between 52.4 and 61.6. So something to notice here is that when we decreased our confidence level, so if we wanted to be 95% confident, it made the range of numbers here smaller. So at a 95% confidence level, we can say that we think P is between 52.4% and 61.6%. When we did a 99.7% confidence level, we could say the range is between 50.1 and 63.9%. So when we're more confident, we have to broaden our range of plausible percentages that agree with that statement. When we become less confident, we can narrow down our range. So we can say, okay, we're less confident, but we think it's between 52.4% and 61.6%, which becomes like more precise. Okay, so how do we go about selecting a margin of error? How do we determine, 99.7%, 95%, 68%, that's going to vary. But when we do want a 99.7% confidence level, we're always going to use 3 standard deviations. When we want a 95% confidence level, we typically use 2 standard deviations or standard errors. And then when we want a 68% confidence level, we go 1 standard error to the right or left of the center. Now, this all comes from the empirical rule. Notice, based on previous observation, which we can flip back to, we can change our confidence level by changing the margin of error. The greater the margin of error, the higher our confidence level will be, but if we make the margin of error too big, we'll lose precision. So the idea here is that we're making a note about how we can adjust the confidence level by changing the margin of error. And let's go back here. So you can see that the greater the margin of error, so this has a bigger margin of error because 3 times 2.3 is pretty big, the more confident we are. But the wider the confidence interval is, the wider range of numbers you have. If we make our margin of error smaller, like this, we have 2 times 2.3, so smaller margin of error here and here. We get a confidence interval that is a smaller range of numbers, but we're less confident in this case. So you want to try to find a balance between having a margin of error that's not too large, but also a decent amount of confidence. Okay, a little bit about notation, and we're going to do an example where we use all of this 2 videos from now. So we write our margin of error as follows: Z star times standard error. So in the examples we just did, we had standard errors of 1, 2, and 3. Well, we only did it for 2 and 3, but you could do it for 1. And no, sorry, that's not standard error. We had our Z star, just rewind the video or don't even think about that. So we had our Z star was 1, 2, or 3. That's how many standard errors. And then if we multiply that by SE, we get some margin of error number. So what do I mean by this? If you do 2 standard errors, then Z star would be 2, and then the margin of error is 2 times the standard error. So just as a quick note, Z star doesn't have to be a whole number. So in fact, you're going to see some examples where we do more than, we do different numbers, not just 1 standard error, 2 standard errors, 3 standard errors. We'll do 1.645 standard errors. And then you would do 1.645 times the standard error. In particular, there's this table in your book you're going to see, and it gives you the different Z stars that you should use for various confidence levels. So if you want a 99% confidence level, you use 2.58. If you want 95% confidence level, we can use 2, but it's actually more standard to use 1.96. And if you want a 90% confidence level, you use 1.645 for your Z star. And then if you want 80% confidence level, you use 1.28 for your Z star. Now, this table is a little confusing, and I'm going to address this again in a video where we actually calculate a confidence interval. But these numbers here are the Z stars. They're telling you how to get it. I don't know what the heading of the column says margin of error is, because you find the margin of error by taking these numbers. They're the Z stars, and then you multiply them by the standard error. Okay, now formulas we'll use. to find confidence intervals. We sort of did this, but not in a rigorous way. So in 2 videos, we'll do it again. We can use these formulas. So the confidence interval is given by this p hat plus or minus m, where m is the margin of error. The margin of error is given by z star times the standard error estimate. So standard error estimate is equal to p hat times 1 minus p hat over n, and then we take the square root of it. So you guys will have to write those down and keep track of them. And just as a quick note, we're using our estimated standard error, so standard error estimate, because we don't know p, so standard error formula requires you to put a p in this spot, but for problems like this, we don't usually know what p is, we only have p hat, so we use p hat to estimate it. Okay, that's it.